In this video, we're going to carry on our study of chemical bonding in the A-level syllabus. As mentioned in the previous video, a lot of new things that we need to learn in the A-level syllabus is for the fact that we need to discuss the factors that affect the strength of intermolecular forces between molecules. And to get there, we need to learn a few new things as shown in the flow chart. So we're going to start with drawing of dot and cross diagram in the A-level syllabus. We have actually already learned how to draw dot and cross diagrams in O-level chemistry. We have learned a sequence of steps that will allow us to draw the dot and cross diagram for ionic compounds and covalent substances. Now in the A-level syllabus, the steps for drawing ionic compounds remain unchanged. So you can use whatever that you have learned in O-levels to draw the same dot and cross diagram for ionic compounds in the A-level syllabus. However, the steps that we learn in O-levels for drawing of dot and cross for covalent compounds, you will find that they no longer work in all cases for A-levels. So let us first recap what we have learned in O-level chemistry to draw the dot and cross diagram for covalent compounds. In this case, we are looking at ammonia. So step number one is to list down all the atoms in the compound. Step number two is to write down the electronic configuration for all the atoms. And step number three is to find out how many electrons each atom needs to share. And that is usually the number of electrons that the atom needs to have a fully filled valence shell. So for nitrogen, that will be 3, hydrogens 1 each. Step number 4 is to find a suitable arrangement for sharing such that it meets the sharing requirements which we have just found out. So the tip is always to place the atom that that needs to share the most in the middle. So in this case, we put nitrogen in the middle and it's surrounded by 3 hydrogens. So if we look at the sharing, we will find that it meets the requirement that we have come up with earlier. Step number 5 is to draw any remaining or non-bonding electrons. What do I mean by that? If you look at nitrogen, nitrogen has 5 valence electrons. It has shared 3, so meaning it has 2 valence electrons remaining. So this is the dot and cross diagram for ammonia. Now let's use the same rules for another molecule called boron. Boron is made up of 1 boron atom and 3 hydrogen atoms. So electronic configuration is as shown. Step number 3, we need to find the number of electrons each atom needs to share. For boron, it is in group 13 or group 3 that we have learned in O-level syllabus. So for elements in groups 1 to 4, they only need to share the group number of electrons. So boron needs to share 3, each hydrogen needs to share 1. Step number 4, to find a suitable arrangement for sharing. Similarly, we place boron in the middle and it shares with 3 hydrogen atoms. Once again, if you look at the sharing, it satisfies the condition that we have earlier established. And step number 5, draw remaining non-bonding electrons. Boron only has 3 valence electrons, so after sharing 3, there isn't any electron remaining. So this is the dot and cross diagram for boron. Now for those of you who are fast enough, you may throw your arms in the air and say, "Sure, this structure is wrong because we don't have a fully filled valence shell around boron." Now you are right. Now, but in the A-level syllabus, we do see quite a number of molecules where the central atom do not have a fully filled valence shell. However, they are stable enough to exist. Some notable examples would be, other than boron, BF3, boron trifluoride, BeCl2, and AlCl3. So if you draw the dot and cross diagram for these molecules, you will find that the central atom would actually have less than 8 electrons or fully filled valence shell. However, they are still stable enough to exist. However, due to the fact that they do not have a fully filled valence shell, meaning they have vacancies for more electrons, they usually undergo further reactions. For example, if you look at boron trifluoride looks like this. This is the structure of boron trifluoride. So there are only 6 valence electrons around boron. So in the presence of, say, ammonia, we have seen earlier that ammonia has a structure like this. It has a non-bonding pair of electrons on nitrogen. So when boron trifluoride meets ammonia, nitrogen or ammonia has non-bonding electrons, has spare electrons. Boron in boron trifluoride has vacant orbitals. So what is going to happen is that they are going to combine to form a covalent bond. Okay. However, this covalent bond is special because typically covalent bonds are made up of a pair of electrons, one from each atom in the covalent bond. However, in this covalent bond, we find that the bond or the pair of electrons come from only one of the 2 atoms. Therefore, we call this, or we give it a special name, we call this a dative covalent bond. All right, or in higher levels, we call it a coordinate bond. The other thing that these molecules tend to form are what we call dimers. So for example, if you look at aluminium chloride, this is the structure of aluminium chloride. Aluminium has only 6 valence electrons, and this means that it has vacancy to accommodate more. So what happens is that when you have aluminium chloride gas coming together, they will actually form coordinate bonds to each other. Okay, bear in mind that there are non-bonding electrons on the chlorine atoms, so the chlorine atoms can actually form a dative bond to another aluminium central atom. Okay, so we call this a dimer because it is made up of 2 molecules of aluminium trichloride. So molecules where the central atom has less than a fully filled valence shell or have less than octet, they tend to either form dative bonds with something that has a lone pair, or they tend to form dimers. Now we'll once again apply the steps that we have learned in the O-level syllabus to another molecule, SO2. This is also the example where we find that the steps that we have learned no longer serve us. It doesn't work for this molecule. So step number 1, we write down all the atoms in the substance. Step number 2, we write down the electronic configuration for each atom. And step number 3, we need to write down the number of electrons each atom needs to share. So in this case, sulfur needs to share 2, oxygen needs to share 2 for each oxygen atom. Now if we look at the sharing requirements, we find that there's no way in which we can find a suitable arrangement for sharing. So from this example, we see that the rules, the sequence that we have learned no longer serves us. So in the A-level syllabus, when we are drawing dot and cross diagram for covalent compounds or covalent molecules, we have to follow a new set of steps. Now we're going to look at the new set of steps for drawing dot and cross diagram for covalent substances in the A-levels. We're going to use it for the same molecule of sulfur dioxide. Now step number 1 is to determine the central and surrounding atoms, meaning for sulfur dioxide, which atom goes in the middle. Now there are a few tips that we can consider in order to know which atom is in the middle. The first tip is that it is usually the element with the lesser number of atoms. So if we look at the formula of sulfur dioxide, there's 1 sulfur atom and 2 oxygen atoms. So that tells us that sulfur is in the middle and oxygen is the oxygen atoms surround the sulfur atoms. Second tip is that it's usually the first element in the chemical formula. So when writing chemical formulas for simple molecules, usually the first atom in the formula the first element in the formula is the central atom. Now there's an exception, which is hydrogen, which is common sense because hydrogen has only one electron, so it's unlikely to be in the middle sharing with many atoms. The last tip is that it's usually the least electronegative element. Now electronegative elements, they tend to hold on to their electrons tightly, they don't wish to share them, so they are rarely found in the middle where they need to share with many other atoms. Step number 2 applies for polyatomic ions, which doesn't apply here, so we're going to skip this step, and when we come to a polyatomic ion, I will describe what these steps mean again. Now step number 3 is to determine the number of bonds each surrounding atom can form, and the rule goes like this. We need to look at the number of valence electrons in the surrounding atom. If the surrounding atom has 1 to 4 valence electrons, then the number of bonds that it can form would be equal to the number of valence electrons. If the atom has 5 to 8 valence electrons, then the number of bonds that the atom can form would be 8 minus the number of valence electrons. Now for hydrogen, it's slightly different because when you have 2 valence electrons, it already has a fully filled valence shell, so the number of bonds that it can form is actually equals to 0. So we have already found out earlier that sulfur is the central atom. It's surrounded by 2 oxygen atoms. So now we need to find out for each oxygen atom how many electrons can it share, or how many bonds can it form. So oxygen has 6 valence electrons, so we have to follow this rule. It means that it can form 2 bonds to the central atom. The other oxygen atom can also form 2 bonds. So for step number 4, now that we have found out how many bonds each surrounding atom can form, step number 4, we need to draw all the bonds to the central atom. So earlier we have found out that sulfur is in the middle, surrounded by 2 oxygen atoms, and each oxygen atom would form 2 bonds to the central atom. So this is how the structure looks like. Step number 5, we need to draw in the remaining or non-bonding electrons. So earlier we already have this structure. In this structure, sulfur has shared 4 of its valence electrons with oxygen atoms. So sulfur is in group 16, it has 6 valence electrons, so it should have 2 electrons that are not used for bonding. As for oxygen, oxygen has shared 2 electrons with sulfur, so it has 4 electrons that are not used for bonding. So once again, this is the dot and cross diagram for sulfur dioxide. We can also represent sulfur dioxide in something called the Lewis structure, where we simply show the bonds present in sulfur dioxide as well as the lone pair on the central atom. So this is called the Lewis structure, which is a simplified dot and cross diagram for sulfur dioxide. Now, once again, students who are observant enough, you might again think that there's something wrong with this dot and cross diagram. Why? Because there are actually 10 electrons around sulfur dioxide. So is that possible? In O-levels, we say that the maximum number of electrons we can have around an atom is 8. But remember, in atomic structure, we have learned that elements in period 3 and above, they actually have your 3d orbitals, which allow the central atom, or which allows atoms of elements in period 3 and above to have more than 8 electrons in its valence shell. So this dot and cross diagram is perfectly okay because sulfur is in period 3. So as mentioned, for central atoms that are in period 3 and above, they actually have d orbitals that can accommodate more electrons. So the number of electrons around the central atoms can be more than 8. Now how do we explain that? We explain that there are energetically accessible d orbitals to expand, which allows the atom to expand beyond octet. So now let us try to use the new rules that we have learned, the new 5 steps to a series of molecules and polyatomic ions. The first of which would be nitrogen dioxide. Step number 1, we need to determine the central and surrounding atoms. Now from the tips that were shared earlier, I think it's not difficult to know that nitrogen is in the middle, surrounded by 2 oxygen atoms. Step number 2 applies to polyatomic ions only, so we are going to skip. Step number 3, we need to determine the number of bonds each surrounding atom can form. So earlier we have seen that oxygen has 6 valence electrons, so each oxygen atom can form 2 bonds to the central atom. Step number 4, to draw all the bonds to the central atom. So oxygen will form 2 bonds to nitrogen, the other oxygen will form 2 bonds to nitrogen. And step number 5, to draw the remaining or non-bonding electrons. Now if we take a look, nitrogen has shared 4 electrons with oxygen atoms. Nitrogen has 5 valence electrons, so there is 1 electron that is not used for bonding. Now at this point in time, you may find 2 things that contradicts whatever that you have learned so far. Number 1 is that the central atom can only have 8 electrons. So if you look at nitrogen, nitrogen has 9 electrons surrounding it, right? And that is a problem because nitrogen is in period 2. In period 2, there are no d orbitals to expand beyond 8 electrons. So in this case, if your central atom is in period 2, you need to apply this rule. Okay, for central atoms in period 2 only, if the number of electrons around the atom is more than 8, then now you need to convert a double bond to a dative bond from the central atom. So what it means is this: we need to convert the dative bond, we need to convert the double bond in this case into a dative bond from the central atom to the surrounding atom. Okay, once you have done that, you can see that now there are less than 8 electrons around nitrogen. We only have 7 electrons. So that solves the problem of not being able to have more than 8. But then there's a second problem, which is this. You may find that there is still less than 8 electron and there seems to be an unpaired electron. So how is this structure stable, or is this structure correct? The answer is yes, this structure is correct. It's stable enough to exist, but like previous cases, since it doesn't have a fully filled valence shell, plus it has an unpaired electron, you can expect nitrogen dioxide to be fairly reactive. So this, as mentioned, this structure is correct. So the dot and cross diagram for nitrogen dioxide would look something like this. Okay, and the Lewis diagram would look something like this. So when we look at the structure of nitrogen dioxide, we find that there is still an unpaired electron on the central atom. So molecules with an unpaired electron are so reactive that we give them a special name. We call them free radicals. So nitrogen dioxide is a free radical. Under certain conditions, it tends to react with itself to form what we call dinitrogen tetraoxide. Okay, so what is happening is that, remember, there is an unpaired electron on each nitrogen, so the unpaired electrons can actually combine to form a covalent bond. This is a very popular reaction in the topic on chemical equilibrium. Why? Because nitrogen dioxide is brown, dinitrogen tetraoxide is colorless. So this is a very popular Le Chatelier's principle question. So now we'll continue to apply the same rules to a few other examples. In this example, we are looking at a polyatomic anion, which is nitrate ion. Step number 1, it's not hard again to know that nitrogen is in the middle, it's surrounded by 3 oxygen atoms. Step number 2, in this case, we have a polyatomic anion. The charge of minus means that we have added 1 electron to the substance. So which atom do we add the electron to? This is where the step number 2 becomes important. For polyatomic ions, in this case we have an N ion, so we need to add electron to the most electronegative atom. In the structure we have nitrogen and oxygen atoms. If you recall the rules for electronegativity, oxygen is more electronegative than nitrogen. So what we need to do now is that we need to add the extra electron to one of the oxygen atoms. Which one, it doesn't matter. So we just need to add the electron to one of the oxygen atoms. Step number 3, determine the number of bonds each surrounding atom can form. So if we look at the oxygen atoms, in general, they can form 2 bonds. Why? Because they have 6 valence electrons. However, there's one oxygen atom that has already taken in 1 electron. So in total, this oxygen atom has 7 valence electrons. So the number of bonds that it can form would be 8 minus 7, which is 1. Step number 4, draw all the bonds to the central atom. So I'm going to draw 2 bonds from each of the oxygen atom. And for the oxygen atom carrying the negative charge, just 1 bond. And step number 5, to draw the remaining electrons. So for nitrogen, you will find that it has already shed all 5 electrons. For oxygen, we need to add in the remaining electrons. So over here, once again, we run into the issue where the central atom has more than 8 electrons. Is that acceptable? In this case, no, because nitrogen is in period 2. So we need to apply this rule once again, because nitrogen is in period 2 and it has 10 electrons in the valence shell. So we need to convert one of them, one of the double bond, into a dative bond from the central atom to the surrounding atom. Okay, so this is the dot and cross diagram for nitrate anion, or if I were to represent it in terms of the Lewis structure, it will look something like this. There. Next, we will look at another example, aluminum hydride. Step number 1, we need to determine the central and the surrounding atoms. Step number 2, we are dealing with a polyatomic anion with a charge of minus, means we need to add an electron to one of the atoms. If you compare the electronegativity of aluminum and hydrogen, hydrogen is more electronegative than aluminum. So we need to add the electron to one of the hydrogen atom. It doesn't matter which one, just add to one of them. Step number 3, we need to determine the number of bonds each surrounding atom can form. So each hydrogen can actually form 1 bond to the central atom. However, there is a hydrogen atom that has already taken in 1 electron. So the number of valence electrons around this hydrogen is 2, and it already has a fully filled valence shell. So this hydrogen can actually form 0 bonds to the central atom. Step number 4, we need to draw all the bonds to the central atom. So we have this, and in this case, we find that there is no bond between aluminum and the hydrogen that has taken in an electron. That's where the special rule comes in. When you have a case like this, you need to draw a dative bond from the surrounding atom to the central atom. Now take note that hydrogen has 2 electrons over here, so you can draw a dative bond to the central atom. Step number 5 is to draw any remaining or non-bonding electrons. So if we take a look, aluminum has already shed 3 electrons, so there are no more remaining electrons. So this is the dot and cross diagram for aluminum hydride, or if I were to draw the Lewis structure, it will look something like this. Next, we look at the example of sulfate anion. For sulfate, the difference is that it has a charge of 2 minus, which means that in total we add 2 electrons to the structure. So let's see how we can do it. Step number 1, we determine the central and surrounding atoms. Step number 2, we need to add electrons to the most electronegative atom. So if we take a look at sulfur and oxygen, oxygen is more electronegative than sulfur. So we need to add the electrons to oxygen atoms. Now the rule is this, that we add 1 electron to each atom. So since there are 2 electrons to be added, instead of adding 2 electrons to 1 oxygen atom, we add 1 electron to 1 oxygen atom each. Step number 3, we determine the number of bonds each surrounding atom can form. So by now it should be very easy to know that oxygen can form 2 bonds. However, the 2 oxygen atoms that have taken in an electron, they can only form 1 bond each because they have 7 valence electrons. Step number 4 is to draw the bonds to the central atom. And then step number 5 is to draw the remaining electrons. So let's check. Sulfur has shed 6 electrons, so there are no more electrons remaining. For your oxygen, there will be some electrons remaining. So once again, this is the dot and cross diagram for sulfate, and this is the Lewis diagram for sulfate anion. Now the last example that we're going to look at is a polyatomic cation, which is the ammonium ion, a very famous ion in the O-level syllabus. So step number 1, we need to determine the central and the surrounding atoms. Step number 2 is going to be slightly different because we are looking at a cation now. Cation with a charge of 1 plus, meaning we need to remove an electron from one atom. So which atom do we remove the electron from? We remove it from the least electronegative atom or element. In this case, comparing nitrogen and hydrogen, hydrogen is less electronegative, so it's easier to remove the electron from it. So which hydrogen atom to remove from, it doesn't matter. I'm going to remove from this particular hydrogen atom, which means that this hydrogen atom now has 0 valence electrons. Step number 3, determine the number of bonds each surrounding atom can form. Hydrogen has 1 valence electron, so they can form 1 bond. The hydrogen with the electron that was removed can form 0 bonds. Step number 4, draw all the bonds to the central atom. So now it appears that we have run into a slight problem where we can't seem to form a bond between nitrogen and the hydrogen with 0 electrons. So that's where the special clause comes in. If you go back to the front where you see step number 4, if you have an atom that has 0 valence electrons, then what do? Is that we need to form a dative bond from the central atom to the atom with 0 electrons. So lastly, we need to draw the remaining or non-bonding electrons. So if we look at the number of electrons around nitrogen, it has 5 electrons, so there are no remaining electrons. Similarly, there are no remaining electrons on your hydrogen atoms. So this is the dot and cross diagram for your ammonium ion, and the Lewis structure would look something like this.